Hi everyone, today we're going to be having a look at magnetic fields and more specifically magnetic force on a current carrying conductor. Okay, so our SACE outline says that the things we need to cover about this topic are the use of the right-hand rule and how we relate the directions of force, magnetic field and conventional current. We also look at the use of the unit of Tesla to measure magnetic field and how to solve problems involving the use of the formula force is equal to current multiplied by the length of the current element and the magnetic field strength and the angle of the field. Alright, so magnetic interactions. When the current flows through a wire, a magnetic field is actually sent up around it. So any moving charge creates a magnetic field. Now, magnetic field lines cannot cross. We know this about how we draw field lines. So as a result, the interaction of these two field lines means that they get distorted. So as a result of the distortion, there is a force that's actually created in this example to the right on the current carrying wire. So if we have a look at it and we have our field going from north to south and we have our current going, let's say, into the page, it would mean that our force is actually going in the same direction as the force arrow there. So because they try and fit around each other, and they're going in the same direction, there's a net force that actually gets exerted on that current carrying wire. Now, in this case, if the field is actually reversed, instead of going from north to south, if it went from top to bottom, then and again, the current went into the page, the force would actually be reversed. And exactly the same thing, if the current was reversed, if we turned our hand around, which we'll cover in a minute, then the current is actually going to be reversed and the force is reversed as well. Alright, so how do we know what direction the force is going to be applied? So there's a rule that we have, it's called a right-hand palm rule, and basically it can tell us which direction the force is going to be applied, or we can work backwards from that and find out either the field direction or also the direction of the current. Alright, so when using the right-hand rule, our palm represents the direction of force. And this is normally the force felt by the current carrying wire. And our fingers represent the magnetic field. Alright, so if our fingers are going in the same direction as the field lines, we place our fingers in the same direction that the arrows are going. Our thumb represents the current, and the direction that the current is actually flowing is the direction we point our thumb. So remember, thumb is current, hand, like palm is force, and fingers actually represent the magnetic field direction. Okay, so what about if the force is going to be on a current that is parallel to the magnetic field? So here, instead of having the wire running perpendicular to the field, it's running in the same direction. And what actually happens in this situation, if we draw our field going into the page, sorry about my crude drawing, in there, and then we have, let's just say we're looking at it from one end, that's going to be our wire heading into the page. Because the wire is actually, the moving charges in the wire are producing their own field, when they're all going in the same direction, they actually fit around each other really nicely. And that drawing doesn't really do it justice, but there's no distortion of the field. One of them's going in, they're going straight, and the one produced from the wire actually fits really nicely around those field lines. So there's no interaction, which means there's no net force. Okay, as a bit of a summary, the magnetic force on a current carrying conductor in a magnetic field, it's at maximum when it's going to be at right angles. All right, so if our field lines are coming across this way, the force is going to be maximum when our wire cuts across at 90 degrees. It's going to be at zero if the magnetic field is parallel to the current. If our field lines are going across this way and our wire is also going this way, it's going to be zero. Anywhere in between, when it's perpendicular and parallel, is going to be of an intermediate value of when the current is at some angle, and I'll show you how to calculate that in a moment. Okay, so be able to calculate what value it's going to be if our wire is at an angle, we need to have an understanding of something called a current element. Now, a current element is a length of wire that is denoted with a delta L for some length of wire. Now, remember, the unit of length is always measured in meters, and that particular wire is going to be carrying some current. All right, and the combination of those, the current flowing through the wire and how much wire is actually in the field, is called a current element. Now, the unit for measuring current element is in amperes per meter, or amps per meter. Amps each meter. Okay, so magnetic field strength vector is denoted as a capital B. All right, now magnetic field strength is the force per unit of current element on a current element that's placed at right angles. So remember, maximum force, and the current element is I times delta L, so how much current is going through a particular length of wire. So the magnetic field is the force felt per unit of current element. Now, the direction of this magnetic field strength is actually found by applying our right-hand palm rule. So the force, remember, was the one denoted by your palm, and the current was by your thumb, and the field was represented by the fingers. So the unit of magnetic field strength is actually measured in newtons per amp per meter, or in a unit called a Tesla. So this is a bit of a summary of that formula. Now remember, it's for a current that's perpendicular to a magnetic field. So if our field is coming across this way, it's for a current that's straight up and down, it's perpendicular. And so we can also remember that F is for the force felt by that wire, I is the current, and delta L is the length of that current element, and B being our magnetic field strength. Okay, but what about if our wire is not perfectly perpendicular, and if it's at some angle to the magnetic field? So to do this, all we have to do is to work out what component of that current element is going to be perpendicular to the field. There's going to be some component. The component that's going to be parallel to the field is going to have no force. So we're not really interested in that one. We're only worried about, if we break down that angle, which portion of that is going to be perpendicular. And we do that by looking at the sign of the angle that the current element is to the field. So we can rearrange our formula by saying that the force exerted on our current element can be found by the current element multiplied by the field strength at that point, multiplied by whichever angle it is perpendicular to the field. So our direction is still found out by using the right-hand palm rule, but it's only applied to the component that's actually perpendicular to the field. So instead of putting your thumb at an angle, you would put your thumb perpendicular to the field and work out, in this case, from my perspective anyway, that the force would be into the screen that I'm looking at. Okay guys, so thanks for watching. Now hopefully you've got a better understanding of how to use the right-hand palm rule. Remember, field, force and current, and you've also understand that the unit of magnetic field is in a Tesla, and can hopefully use the formula that we have now to solve problems involving current elements in magnetic fields.